welcome everyone. My name is Annandale. I'm one of the founders and the president of the Nobel Astronomy Club. In the name of the club, I would like to thank the staff, faculty, administrators, our advisor, Dr. Peter Williams, and the Annandale Student Life for their support of this event. Today, the Astronomy Club and the Annandale Student Life are honored to host a lecture about quantum information, a scientific and technological revolution for the 21st century by the Nobel laureate in physics, Dr. William Phillips. Dr. Phillips graduated from Juniata College in 1970, summa cum laude. After that, he received his physics doctorate from the Massachusetts Institute of Technology. And in 1978, he joined NIST. He is currently a distinguished university professor at the University of Maryland. In 1997, he won the Nobel Prize, which he shared with Claude Cohen-Tanuj and Stephen Chu, for the development of methods to cool and trap atoms with laser light. Today, he will talk about the effect of the discovery of the quantum nature of the submicroscopic world and the advance of information science and engineering have had not only in our daily lives, but also in our worldview. Please welcome Dr. William Phillips.
Well, thank you very much. It's a pleasure to be here. As you can see, I'm from the National Institute of Standards and Technology. I'm also from an organization called the Joint Quantum Institute, which is a joint operation of NIST and the University of Maryland, and that's how my University of Maryland connection comes in. But I'm still an employee of the U.S. government, so it's really NIST that is my home. And over the years, the work that I'm going to be telling you about has been supported by NIST and through the university, by the National Science Foundation, as well as by DARPA. So let me just say a word about the relationship with the University of Maryland. We've formed this Joint Quantum Institute in 2006, and we were fortunate enough to get funding for a Physics Frontier Center at the Joint Quantum Institute from the National Science Foundation in 2008. And a lot of the work of the Physics Frontier Center and of the Joint Quantum Institute is related to quantum information, which is the subject of today's talk. Quantum information, a scientific and technological revolution for the 21st century. So what am I talking about? Well, in the 20th century, there were a number of revolutions that were both scientific and technological. Quantum mechanics was one of those revolutions, and information science was another. I really think that these were two of the most important revolutions that happened in the 20th century. Quantum mechanics changed the way we think about the physical world. It changed the way we think about the nature of reality, as we're going to see in just a little while. Information science changed the way we think about thinking. As a result of information science, we have machines now that do the kind of jobs which in times past were thought to be the province of thinking human beings. And now we have machines that do those kinds of jobs. And interestingly, the only reason why such machines are possible is because of the things that we learned about with quantum mechanics. So these two revolutions are tied together in an intimate way in the 20th century, but in the 21st century, they're coming together in a different way, where quantum mechanics and information science are joining together to form a new science, namely quantum information science. Now, to understand what this is all about, let's think about those revolutions of the 20th century. In particular, let's think about the quantum revolution. What happened in the 20th century? Really, at the very beginning of the 20th century, what happened to change the way in which we think about the physical world? Well, before that, we had classical mechanics. This is the mechanics of Sir Isaac Newton. It describes all kinds of things. The motion of the planets, for example. The behavior of billiard balls, one of the favorite icons of physicists, and lots of other things, the kinds of things that made up the Industrial Revolution. So the ability to make things like automobiles and steam engines was because of our understanding of classical mechanics. A few years ago, I attended a meeting about quantum information in the Swedish city of Göteborg. And as is often the case at meetings like this, we had an excursion. And the excursion took us on a 19th century steamboat out onto the water of the harbor of Gothenburg. And because we were physicists, they invited us down into the engine room, thinking we'd be interested in seeing the engine room. And this is a little movie clip from the engine room. This is the chair of the conference. And the thing that struck me about this was there were all these wonderful things going on in the engine room. Oops. So let me run the movie. All of this is stuff that you could understand with classical mechanics. All of these gears and these pistons and all the linkages. This was, in a certain sense, a wonderful expression of the success of classical mechanics up through the 19th century. Now, if you want to be honest about it, classical mechanics couldn't explain why these metals were shiny. It couldn't explain why those metals were hard. It couldn't explain why the solids were solid. But all the ways in which these things moved could be explained by classical physics. And now we come to quantum mechanics at the beginning of the 20th century. And people like Bohr and Heisenberg and Schrödinger develop a new understanding of physics that explains the behavior of the submicroscopic world, the behavior of atoms and molecules and their constituents. And this turned out to be essential to understand all kinds of stuff, to understand chemistry, the nature of materials, as I said, why things are shiny, why things are hard, why things are soft. You needed quantum mechanics to understand that. And it led to things like semiconductor electronics. Were it not for quantum mechanics, we wouldn't have things like transistors, and certainly not things like computers and iPhones and all the things that are so much a part of what we consider to be our modern technological lives. Well, what is it about quantum mechanics that's different from classical mechanics? Well, one of the things that quantum mechanics teaches us is that everything has a character of being both a wave and a particle. So before the development of quantum mechanics, people thought of atoms, if they even believed in atoms, because at the beginning of the 20th century, a lot of people didn't believe that matter was made up of atoms and molecules. It took Einstein's theory of Brownian motion to finally convince people that that was true. But if they believed in atoms, they thought of them as being particles. And what quantum mechanics taught us was that we should think of these things as waves. And people thought of light as a wave, and quantum mechanics taught us that we should think of light as particles, that we should think of everything as both particles and waves. And there's a wavelength associated with that wave nature, and it's equal to Planck's constant divided by the momentum of the object, be it light or something like a billiard ball or an atom. Now, the point is that Planck's constant is really, really, really small. And what that means is for any reasonable number for the momentum, like the kind of momentum that you might have for a billiard ball rolling across a billiard table, the wavelength associated with it is going to be ridiculously small. So for something like a billiard ball, the wavelength that's associated with its motion is on the order of 10 to the minus 30 meters. Now, to give you an idea of how small that is, I mean, you know how big a meter is, right? So now you go 15 orders of magnitude smaller than that, and that's the size of a nucleus, which is already something like 5 orders of magnitude smaller than the atom itself. And then you go another 15 orders of magnitude smaller than that, and that's the wavelength of a billiard ball. The point is, you just don't care. It's just too small to matter. So nobody wants to do quantum mechanics with billiard balls because there's no need to. The wavelength is so small that it simply doesn't matter. But if you ask what is the wavelength of an electron in an atom, you find out that its wavelength is about 10 to the minus 10 meters, which is the size of the atom itself. So it matters big time that the electron is a wave because its wavelength is the size of the object in which the electron lives. So it's really important. You cannot ignore the wavelength, the wave nature of electrons, or you simply can't understand at all how atoms work. And we've known that since the early part of the 20th century. But there's more. Let's start with an electron. An electron is a really weird particle. It's one of the fundamental particles of nature. Its size is 0. That's the diameter of an electron, 0. All the best measurements that we've made on electrons lead to the conclusion that its size is 0. In spite of that, it spins on its axis. Now, that's a stupid statement to make, right? Because how could it possibly have an axis if its size is 0? Nevertheless, it is spinning. That is, it has angular momentum. It acts in all the ways that you expect a particle that has angular momentum, as if it were spinning, to behave, yet it has no size. How can that be? Well, I have no good answer for that, but that's the nature of electrons. And, but there's more than that. The direction in which the axis of this electron is pointing, in other words, the direction of the angular momentum, for any ordinary object, like, say, a spinning gyroscope, you could turn it any way you wanted, and you could make the projection of the angular momentum vector on some chosen axis be anything you wanted it to be, depending on what angle it was making. You could make that angle anything you wanted. With an electron, you can't do that. There's only two possibilities for the projection of the angular momentum of the electron on any given axis, +1/2 and -1/2, where the half is the fundamental unit of angular momentum, which turns out to be Planck's constant divided by 2 pi. So that's strange, that the projection of the angular momentum of the electron cannot be anything you want as you might imagine it, but in the world of quantum mechanics, it's only got two possible values. Now, there are other things that also have spin in quantum mechanics, and they have also what we call quantized projections of angular momentum. Not always just plus and minus of half. It depends on how big the angular momentum is. But what we say is when it's +1/2, we say the spin is up, and when it's -1/2, we say the spin is down. And those are the only two possibilities. But it gets worse than that. The electron can be in both of those states at the same time. That is, it can be pointing both this way and that way. Now, how is that possible? I mean, we go around saying you can't be in two places at the same time, but an electron can literally, and I'm using literally in the literal sense, okay? An electron can literally be in two places at the same time. I mean, not only can it be both up and down at the same time, it could be here and here at the same time. This is a property of quantum mechanics that we call superposition. And it's just strange. And there's no way that I can tell you how such a thing is possible, that you could have an object that can be both here and here at the same time, or be pointing both up and down at the same time. It's not like it's in between. If you measure where it is, you're always going to get up or down. But before you measure it, there's no way of predicting what it's going to be. But there is a way of showing that it's not just up or down and you didn't know beforehand. There's a way of showing that, in fact, before you measured it, it was both. Now, I can't explain how that happens, but I can give you a funny sort of analogy. You've all seen pictures of cubes like this, right? Now, one of the great things about a picture like this is that it's ambiguous. You can imagine that this square right here is the front that's facing you, that's furthest toward you. Or you could imagine that this is the face that is towards you. So it could be one or the other of these. And you know that if you look at this for a while, you can make it switch back and forth. So sort of the way in which that cube turns out to be is sort of your cognitive choice of the way you want to make your brain see it. So it's not a very good analogy, but it's a kind of an analogy to what happens in quantum mechanical superposition. Before you look at this thing, and before your brain decides which way it's going to be, it's both at the same time. And this is, you know, as I said, there's no real good analogy, but this is the closest classical analogy that I can think of. Now, a number of you may have heard of Schrödinger's cat. So Schrödinger's cat is this kind of idea of an electron being in two places at the same time or being up and down at the same time, sort of writ large. The idea is that Schrödinger imagined that he might put a cat in a box, and then some mechanism that could kill the cat would depend upon whether, for example, the electron were up or down. And the electron would be in a superposition of being these two states, and then you wouldn't know whether the cat was alive or dead because of this superposition. And so the cat itself would be in a superposition of being alive or dead. Of course, no one's ever seen or been able to do any experiments on a cat that's actually alive or dead, but it's made for a lot of wonderful jokes. And this one appeared in the New Yorker just recently, making fun of this idea of Schrödinger's cat. Now, okay, so superposition, now we're really getting into the weird part of quantum mechanics. But it's still not the end of how weird quantum mechanics is. There's another thing called entanglement. Now, entanglement is something that comes about when I have two particles. So let's imagine that I've got two particles. They could be electrons, they could be atoms, it doesn't matter, but they have some sort of spin. And this particle could be spin up or spin down, and this particle could be spin up or spin down. And now I want to describe the state of the two particles together. And one of the possible things is that when this one is up, this one is down, and when this one is down, this one is up. Now, there's no way of knowing before you measure it whether this one is going to turn out to be up or down. It's going to be a 50% chance if they're in an equal superposition. And the same is true of this one. There's no way of knowing beforehand whether you're going to measure this one to be up or this one to be down. But if you measure this one to be up, sure as heck this one's going to be down. In other words, the fate of these particles upon measurement is entangled. The two fates are entangled. You don't know what either one of them is going to do, but their fates are entangled. And the weird thing is that this happens even if these two particles are widely separated, so there's no possible way that this particle could communicate with this particle and tell it somehow that it should be down. It's absolutely impossible. You could have these things a light year apart, and if you measured this one, immediately you would know that this one would have to be down. How could that be? It's bugged Einstein because, of course, Einstein's theory of relativity says that nothing, no information could be transmitted faster than light, and so this sort of bugged him that this would happen according to the rules of quantum mechanics, which he understood quite well. He never liked them, but he understood them probably better than most people. And one of the things he understood about quantum mechanics was that it would allow this kind of foolishness to go on. And so he, with his colleagues Rosen and Podolsky, wrote a paper in which they described, not exactly what I've described here, but something similar to it, and said, this is just silly, this can't be. There must be something wrong with quantum mechanics. There must be something else that we're going to have to add in to quantum mechanics to make this foolishness go away. Well, it turns out that's not true. This foolishness happens, and people have measured again and again that exactly this sort of foolishness happens. So here's a kind of a cartoon version of the experiments that people have done to show that this kind of foolishness does indeed happen. So you imagine here you've got some kind of a composite particle that's got two things, one of which has spin up and the other which has spin down, and it has this state that says if the one that's going to go this way, you're going to break this thing apart and send one to the left and one to the right. If the one going to the left is up, the one going to the right is down, and vice versa. And so someplace very far away, you're going to have a detector. The detector is going to tell whether the spin is up or down. And once this detector tells whether the spin is up or down, there's no more uncertainty. The value of the spin is set in concrete. And that's why I've drawn a concrete block here, so that we can see that we've made the value of the spin concrete. And once that's done, if this is up, that one's down. And if this one's down, that one's up. And if I was being completely honest, which I'm not, then I would have to tell you that in order to really see the weird part of it, I've got to have a detector here that measures along some axis, and the detector over here should be tilted and measure along a different axis. And then you can show that what quantum mechanics predicts is something that's impossible to happen if you believed that when this particle headed off to the left, it had a value for its spin, that it actually existed before it was measured. And if this one going to the right, if it actually existed before it was measured, what quantum mechanics predicts would happen could never happen if those things were fixed at the time of the birth of those two particles. And experiments have been done and found that quantum mechanics is the right answer and your classical intuition is the wrong answer. So quantum mechanics really is that weird. Now, Einstein died before those experiments were done, but I really wonder what he would have thought from those experiments. So, as with the case of superposition, I've got a bad classical analogy. If you have two of these ambiguous boxes, at least when I look at them, I tend to see both of them the same way. If I see this one with this face to the front, I see this one with it face to the front. So I either see this or this. In other words, the fate of the two boxes is entangled with the way I see them in my brain. Maybe you can decouple them, but that's the way I see it. Now, why do we care about all this? Well, one of the reasons we care about all this is because all of this thinking led to our modern technology. But for this talk, the reason why we're interested in it is because we are going to use these quantum mechanical objects as the carriers of information that we call quantum information. And that quantum information is going to be able to be processed in ways that are very different from classical information. In fact, it is so different from classical information that I claim that if I could make a computer that used quantum objects as the carriers of information, what we call quantum bits. You know that your computer processes everything in bits, and those bits are something physical, and we'll talk about that a little bit more in a moment. But if instead we did it with quantum bits or qubits, we could make a different kind of computer, and that computer, if we could make one, and so far we have made sort of baby versions of quantum computers, but that computer, if we could make one, would be more different from today's high-speed digital computers than these computers are from the ancient abacus. That's how big a paradigm change I'm talking about for having quantum information. So let's talk about what quantum information is. Okay, let's talk about classical information first. So in classical information, we have bits that are either 0 or 1. And I could represent that 0 or 1 by anything that's in two possible states. It could be spin down and spin up, for example. And these things are stored and processed in your computer as physical things. So this bit could be a transistor that's a switch that is either turned on or off. It could be magnetic material on a hard disk that is magnetized one way or the other. It could be a spot on a CD or on a DVD that's either burned or not burned. And the great strength of digital information is it's either one thing or the other. There's no ambiguity about whether that spot on the CD is burned or not burned. And unless you start scratching your CD and going at it with sandpaper, it's really good. And that's why digital music is so high quality, is because there's no ambiguity about what the nature of that bit is, no ambiguity about whether that transistor in your computer is turned on or off. So you can really rely on your computer doing calculations the way it's supposed to. That's classical information. Digital is really important. And it's so important that you can get T-shirts that say this on them. Okay, so what about quantum information? That was supposed to be funny, by the way. Now, I realize that I am a physicist. I'm not a stand-up comedian. But, could you give me a break here? You thought it was funny, right? Okay. So, quantum information is some kind of a physical object, like, say, an electron, that could have one state spin up and another state spin down, which could represent the zeros and ones. But the difference is It could be in a superposition of those two states at the same time. So now, instead of having bits that are either 0 or 1 quite firmly, you have bits that could be both 0 and 1 at the same time. Now that sounds like a disaster, because the great power of digital information was that it was either one or the other. But it turns out that there are some wonderful things that happen when these quantum bits can be both at the same time. So let's, and entanglement is one of the key things that makes this happen. Let's imagine a classical memory register that has 3 bits in it. Now 3 bits is nothing, right? I mean, your computer comes with gigabytes, so 3 bits is nothing. But if I have a 3-bit register, then you know that I can represent, in that 3-bit register, I can represent any number from 0 to 7. So 8 different numbers. This is 5, right, in binary. A 1 in the 1's place, a 0 in the 2's place, and a 1 in the 4's place. That's 5. And I could have any number from 0 to 7 could be represented in this. But if these were spins, like electron spins or atomic spins, any kind of a quantum mechanical object that could be in one of 2 different states, then it could also be in a superposition of all 8 of those different numbers. And here is an expression that shows one of the possibilities, well, the most general possibility, in fact, where I've got some coefficient times all zeros, some coefficient times 2 zeros plus a 1, all the way up to some coefficient times 3 ones. And I could have a completely general state. It could be any value of these coefficients, any complex number for those coefficients, as long as the sum of the squares equals 1, because there's only one of these registers. And in general, such states are highly entangled. So for example, I could have a superposition of 0, 0, 0 and 1, 1, 1. That's a highly entangled state, because it says if I take the first bit and find that it's 0, then I'm going to find that all the other bits are 0. And if I take the first bit and find that it's 1, then the other bits are going to be 1. So it's a highly entangled state. But here's the deal. If I've got an n-bit register, then classically I can store 1 n-bit number. If I've got a quantum mechanical n-bit register, then I can store 2 to the n. So for 3, 2 to the 3 is 8. You know, if this had been 4, then it would have been 16. I can store 2 to the n n-bit numbers all at the same time. Now, imagine that I had a 300 qubit register. That's not very many bits, right? 2 to the 300 is a number that is larger than the number of atoms in the entire universe. So that means with a single 300-bit register, I could store more numbers simultaneously than there are atoms in the entire universe. Now, if I measure it, I'm going to get one of those 2 to the 300 numbers. But if I don't measure it, then it still has all those 2 to the 300 numbers. And if I then process that bit or that register with some kind of a quantum processor, it's going to be doing a calculation with all those numbers at the same time. And if you're clever enough, you can come up with an algorithm that will do something useful. It turns out nobody's come up with an algorithm for doing arithmetic better with a quantum computer, but there is a wonderful algorithm. The algorithm is for factoring numbers. Factoring is hard. Here's a number, 6-digit number. I defy you, without using a hand calculator, to just look at that number, unless you're one of these people who can do amazing calculations in their head, to look at that 6-digit number and figure out what its 2 prime factors are. That's a hard problem. A computer could do it pretty quickly, but it's kind of hard for a human being. I mean, the computer would just search through the possible prime factors until it found them. Any elementary school student could multiply these 2 prime factors together to get this number. No problem at all. So we have this asymmetric problem, because factoring and multiplying are the inverse operations of each other. Now, why is that interesting? It's interesting because you can use this asymmetry, the idea that it's easy to multiply and hard to factor, to transmit secret information. When you go online and you want to buy something from one of these online companies and they ask you for your credit card, unbeknownst to you, but being done in the background, is they're sending you a number to which they know the factors and no one else does, because it's so big that nobody can factor this number. What I neglected to tell you is how hard it is to factor things. The difficulty, that is the amount of time it would take a computer to factor a number, is an exponential function of the number of digits. So that's what is technically called a hard problem. So all you have to do, if it's not hard enough, just add a few more digits, and then no computer that we have will ever be able to factor it. So Amazon sends you a number, your computer uses that number to encrypt your credit card and sends it back to Amazon, and nobody who intercepts that message can tell what your credit card number is, because they can't factor the number that Amazon sent you. Now, I'm not sure what kind of security Amazon uses or anybody else online. People who are sending military and industrial secrets and diplomatic secrets use really long numbers. The fact is, you don't have enough money that anybody cares that much about your credit card, right? I mean, they're not going to go to the great lengths that people do to try to protect diplomatic secrets, for example. But the point is that today, people are exchanging information all the time by what's known as public key encryption. And that means that everything is done publicly, and the only secret is that one of the people knows what the factors are to a big number. And this really makes things a lot easier when you want to share secrets, because you don't have to send some spy, with a briefcase handcuffed to his wrist with the keys to some secret code. You can just send it in the open, and as long as nobody can factor the number, then you're fine. Well, here's the problem, or the solution. If you had a quantum computer, you could factor those numbers. The guy named Peter Shor, back in 1995, figured out an algorithm where he showed that if you had a quantum computer where the bits could be in superpositions with each other, you could factor a number in what's called polynomial time. That is, the amount of time it takes the computer to do the calculation only grows like a polynomial, in this case like the third power of the number of digits. That's called an easy problem in computer lingo. So that's a big deal. And people are really, really interested in that because, well, you can imagine, right? If you had a quantum computer and your enemies are communicating with one another using public key encryption, you could read their messages. So you can bet the spies are really interested in this. This is really the killer app for a quantum computer. Now, we don't have a quantum computer that can factor numbers that we can't factor with a regular computer yet, but this is one of the reasons why people are so interested in this whole idea of quantum information. And it has captured people's imagination so much that science fiction stories have been written about it. This Tom Clancy novel called Night Moves involves an evil protagonist who builds a quantum computer. And one of the things I like about it is he sort of explains to his cohorts how he came to this, and talks about how back in the old days, Dave Wineland and Chris Monroe made some of the first steps toward making a quantum computer. Now, I understand that Dave Wineland came here and gave a talk in this same forum, and sure enough, Dave Wineland is one of the great pioneers of this idea of quantum information. And Chris Monroe used to work with Dave Wineland, now my colleague at the University of Maryland in the Joint Quantum Institute. So I know both of these people really well. And in the book, this evil protagonist is asked, okay, well, why have you been able to make a quantum computer when everyone else is still struggling? And he says, because I'm so much smarter than those guys. I know those guys. I don't think anybody's very much smarter than them. But it made a great science fiction story. But the point is that it's not just science fiction. A lot of people are interested in quantum information for doing real hardcore research. Why? Well, there are important applications, not just factoring numbers. If you had a quantum computer, you would be able to solve quantum mechanical problems that ordinary computers can't solve. If you have, for example, a quantum mechanical system that has 50 spins that are all interacting with one another, if you want to do a brute force calculation of that, there is no computer capable of doing that, because the difficulty of that problem grows like 2 to the 50th, okay? And 2 to the 50th is too big a number for any computer that we have to deal with. But if you had a quantum computer, it could do that kind of a calculation quite easily. So that's a really important application beyond the killer app of factoring numbers. Another reason why people are interested in this is that quantum mechanics uses, quantum information uses these really weird aspects of quantum mechanics, superposition, entanglement, these kinds of things that bummed out Einstein. And a lot of people wonder, as Einstein did, can it be true that quantum mechanics really is so weird and so counterintuitive? And working in quantum information puts you in contact with these really strange ideas that if you believe in quantum mechanics, you believe are true, but a lot of people want quantum mechanics to fail because they want something that's more understandable. And there are a lot of experiments that could be done if you had a quantum computer working that could answer some of these questions that people have posed about the possibility of quantum mechanics failing at some point. So I've already mentioned the computation power for interesting problems is astounding. Factoring, and it's not just factoring, but there's a number of other problems that fall into the same class of problems where Shor-like algorithms can solve them. And this is a really interesting situation because you've got a problem that has a certain complexity class, it's hard or easy. And changing the physical platform on which you do the calculation changes the complexity class. This is something that's really astounding to computer people because that's not supposed to happen. But of course, that's not supposed to happen in a world where you don't count the possibility that things might be quantum mechanical. And this leads to the possibility that it might be true. Not very many people believe it, but we don't really know that it's not true. It might be true that quantum computers could solve general hard problems. There's a whole class of hard problems in mathematics that computers can't solve. And if you could solve them, it would really change things in a dramatic way. This is something that was said about this by Michael Friedman, who's a winner of the Fields Medal, which is sort of like the Nobel Prize for mathematics. And he said, if you had a machine that could solve a particular class of hard problems, then among its minor applications are that it would supersede intelligent, even artificially intelligent proof finding with an omniscience not possessing or needing understanding. I don't have any idea what that even means, but it sounds really, really cool. And if it were true, it would really change things. Okay, so quantum computers, a couple of killer apps. Here's another killer app for quantum information, not for quantum computing. Communication. Classical communication. We always talk about the sender as A, or Alice, and she has some message, which is in this case, our 3-bit number, here 5, and she wants to send that message to Bob along this communications line. Now, I like to anthropomorphize these senders. So here's Alice, and following along the same lines, here's Bob. So Alice sends Bob this 3-bit message. So the problem with this kind of communication is that there is an eavesdropper who is known as Eve, obviously, and Eve taps the phone line. You probably know we have some three-letter agencies who do this to us all the time, right? So, so people know that this happens. It happens all the time, that somebody taps the phone line and gets the message. So if Alice wants to communicate some secret message to Bob, then the two of them have to worry about the possibility that Eve is tapping the phone line. And sure, they can send their thing through public key encryption, and then nobody will be able to break the code. But what if somebody makes a quantum computer? They're storing, they is storing all this information, and if somebody makes a quantum computer, then they can factor the number in the public key encryption, and they can find out what the secret was, and maybe 20 years from now, secrets that nobody wanted to be known and are still sensitive enough that you don't want anyone to know them. And there are secrets like that, believe me. I have no idea what those secrets are, but I can tell you for sure there are such secrets that even 20 years later, people don't want anybody to know what those secrets are. And then you could find out what they were. And so people are worried about this, that they would like to have another way of having secure communication that, that couldn't be attacked by any kind of numerical attack. Now, of course, you can always send your secret agent, with the briefcase, but you don't know what happens to the secret agent on the way, right? So nobody's really ever sure about that way of communicating secrets. And so people ask, could we use quantum mechanics to ensure the security of our transmission of information? So in the quantum mechanical version of this thing, Alice has two entangled bits. One of them is up or down, and the other one is down or up. And neither she nor Bob will have any idea what those are going to be until they're measured. And what she does is she sends one of those bits to Bob and keeps one for herself. Now, when she measures her bit, she knows what Bob's bit is going to be, and they can compare. She can say, Bob, you got that bit? He says, yep. And she says, I measured that one. And he says, yep. And she says, okay. And this is all done in the open. Make that the first digit of our encryption key. Done. Nobody can tell. What if Eve tries? She can't. Because there's a theorem in quantum mechanics that says you cannot reproduce a quantum state. If she takes this thing here and then tries to send on a copy of it to Bob, it's not possible. By comparing results in the open of things that they both measured, Alice and Bob can tell if somebody is messing around. So it becomes a tamper-evident way of communicating. You can confirm that nobody has tampered with the data, and then you can use some leftover stuff to create your encryption key. So this is another killer app for quantum information. And this is a reality. You can buy a machine that does this. It only works at a few bits per second, but in our laboratories at NIST, we have on the 12th floor of an 11-floor building, we have a laboratory where they are transmitting quantum key at streaming video rates. So this is the real deal. You can make a lot of key for secret information. Okay, so now, real qubits. I've talked about these things as if they were electrons. Rarely are they electrons. Very often, they're photons. So single particles of light are the things we use for communication. And they have this wonderful feature that they can have different polarizations. You could have the electric field of the photon pointing this way or this way, and those become the two states. Or you could have them circularly polarized, so they're spinning this way or spinning that way, and those are the two states of your qubit. You could have quantum dots, nanofabricated devices on semiconductor chips. Single Cooper pair boxes. These are superconducting devices where you can tell whether or not a single electron or a single pair of electrons has gone on or off. And it could be in a superposition of being on or off. And these things are not quite as small as atoms, but they're small enough to exhibit these quantum mechanical behaviors. You could have other kinds of superconducting circuits where you had a ring of superconductor, and you could have a current going around that ring, and the current could be going around the ring in one direction, or in the other, or in both directions at the same time. It's one of those wonderful quantum mechanical things where it can really be doing both things at the same time with a macroscopic current. Single atoms that are implanted in solids could be qubits and are being used for qubits. Single isolated ions, this is what Dave Wineland does in his laboratory. And I suspect that he talked to you about those single ions and how they could be storing quantum information. Single isolated neutral atoms held in vacuum. This is what we do in my laboratory and in a number of laboratories in the JQI. And the JQI also does ions. So these are among the ways in which you might make quantum bits, and people are doing this all the time. And here is a simplified version of the sort of thing we do in my own laboratory. We have an atom. I've drawn a very simplified version. There's a nucleus that has a spin. There's an electron that has a spin. And you could have two different kinds of states of the atom, one in which the two spins are pointing in the same direction, one in which they're pointing in opposite directions, and these represent two different energies for the atom, and you can use these two different energy states as your qubits, and we do that in our laboratory. Now, if you want to do a computation, you've got to have more than just bits. You need something that can perform logical operations, and this is just like what happens in your computer. If you want to add two numbers together, here you're adding together 5 and 1, so this is going to add up, and you're going to get 110 for 6, and you're going to have some kind of a processor that can add binary digits together, and you know, obviously your computer has those kinds of things in it. Well, we have to have something analogous. It's not an adder. What we want is something that can entangle two qubits. So one of the possibilities is to have the two atoms held next to each other. They're only about a micron apart. Then we can change the spin of one of the atoms, so the red indicates that its spin is changed. We can put the two atoms together by distorting the little micro traps that are holding these atoms. We can put them in the same trap, and that will entangle them, and then we can pull them apart. And we've done that experiment, and here is a movie that sort of shows that. We change the state of the atoms, turning half of them into a different spin state. We then bring them together, and then when they're together, they swap the information back and forth. And if you stop that halfway in between, it's what we call square root of swap, and that is an entangled state. And then you can separate the atoms, and you've got what we call a quantum gate, something that will allow you to do a wide variety of quantum computations. Here's an example of the kind of thing we dream about. So you imagine that you have a whole bunch of atoms, and you're holding them in an array of microtraps, which we make in our laboratory all the time, and then you manipulate them with laser beams, changing the state of some of them, and then grabbing a hold of some of the atoms so that you can move them to a place where you might want to process them. So we can shine in a laser beam and pull an atom to a processing area, pull another atom, any one we want, to a processing area, change its state, then bring those two atoms together with another laser beam and have them undergo an entangling operation, and then replace those atoms back in the places where they came from. So by doing these kinds of operations, we can imagine doing the most general sorts of quantum computations. Now, when are we going to have a real quantum computer? Now, what do I mean by a real quantum computer? Well, there are lots of things that you might imagine are a real quantum computer. A small-scale processor, something that's got about 10 qubits, that could act as a quantum repeater. What do I mean by a quantum repeater? Let's say that Alice and Bob are communicating with each other, and they're kilometers apart, and they're sending their information over some sort of an optical fiber, and they want to make sure that Eve hasn't tapped into the fiber somewhere along the line. Now, the trouble with these optical fibers is they're not perfectly transparent. There's a little bit of loss. And so if they're 100 kilometers apart, there's a good chance that they're going to lose the single photon that is the signal. And so you got to do something to allow them to be separated by that distance. Now, you can't just put an amplifier in there because you already know that you can't duplicate a quantum state, and that's what you want to do, but it's not going to happen because it's not possible. But there's something more sophisticated that you can do. Instead of sending 1 photon, you could send 10 photons. And somehow you store only 1 bit of information in those 10 photons. It has to do with the relationship between those photons. And the great thing is that if you do this right, you could lose 1 of those photons, and it would still be okay. You could still reconstruct what was going on. Simplest thing to imagine is this. Let's say you had 10 what we call physical qubits, and you want to store 1 what we call logical qubits. Well, you could do it by making every one of them the same. So you got 10 things are pointed up, and or all 10 are pointing down. Now, let's say you lose 1 along the way. You still got 9, so you know what it is. So it's okay. Well, it's not that simple, but that's the general idea. There's a thing you can do to find out what, whether an error occurred and to fix it. And this is really important. You have to find out that an error occurred. You have to fix it without learning what the value of the qubit is. Because if you learn what the value of the qubit is, then it's collapsed into some state, and you don't have this wonderful superposition anymore. But it turns out that there's a process, a number of different ones that people keep inventing new ones that can do that if you've got a number of qubits. But you need some processor that can figure out if an error happened, fix it without finding out what the value of the qubit is. And that's what a small processor could do. We're pretty close to making those things. We have, you know, in Dave Wineland's laboratory and in Chris Monroe's laboratory, they've got more than 10 qubits, and they're talking to each other, and they're able to process information. All we have to do is solve some problems about getting the information in and out, and we'll be able to have a quantum computer. A larger scale computer that could factor numbers that can't be factored by any computer, even any computer of the future. So imagine you project yourself 50 years into the future, and you ask what kind of classical computers we're going to have, and then say, I want to be able to factor a number that that computer can't factor. Okay? What are the chances that we're going to have such a computer? And I say it's about 50-50. I think there's a 50% chance we'll have a computer like that in 50 years. Some people think that it might be possible to have one in 20 years. Almost nobody thinks we're going to have one faster than that. So this is a really hard problem. And people are working on it in laboratories all over the world because it's such an interesting problem, both from a practical point of view and from the point of view of fundamental physics. But it's a hard problem, and it's not something that's going to happen overnight. One of the real problems is this. I told you you dare not measure what the qubits are. But it's worse than that. You dare not allow the qubits to come in contact with the environment, because that will mess them up just as surely as if you had measured them. So let's say I've got a qubit that's both a superposition of being up or down. If I allow it to come in contact with the environment, in other words, I allow light from the room to shine on this qubit, and that light has the possibility of flipping what spin it's in, and it does that in a random way because the light in this room is so random. Well, that's going to mess things up. We call that decoherence. It's going to be a disaster, and I have to protect my atoms from that, or whatever I have. And fortunately, our atoms are relatively easy to protect. We can protect them for many minutes, even hours in some cases. But when you protect them that well, then it's really hard to do anything to them. And so we have this constant struggle between the desire to protect our qubits and our desire to manipulate them. And whenever we manipulate them, then we open them up to the possibility that they're going to get messed up. So, so this is a real problem, and it's one of the reasons why we don't have really good quantum computers right now, is because we have to solve these problems. But the fact of the matter is, we're getting better at doing that all the time. On the other hand, there's another thing called quantum simulation. I told you that one of the great things about a quantum computer is that if you had one, you could do all kinds of quantum mechanical problems. But it turns out you don't really need to have a general purpose quantum computer to do interesting quantum mechanical problems. If you just had a whole bunch of qubits and you could arrange for those qubits to interact with each other in the way that particles in nature interact with each other, then you could solve quantum mechanical problems that no computer can solve just by letting your qubits evolve and seeing what happens. And this is called quantum simulation. And we're already doing that sort of thing, and we're already just on the verge of solving problems that no computer could possibly solve. We're just at that limit now. And in a few years, we'll definitely be solving problems that no computer of today or of a few years from now will be able to solve. So this is something that's a reality today. And thinking about quantum mechanics in this quantum information way has given people a new window onto the kinds of problems that disturb people about quantum mechanics. Well, I'm pretty much coming to the end of this. There's a few other things that I might tell you, but let me just go to the, well, I guess I've already said all this. You know, there's some experiments that we're doing that are sort of in this quantum simulation business, but I don't really have enough time to tell you about them. The point is that I want to make is that this is a really exciting area. And in my laboratory, we have a collection of people from all over the world who are working on various aspects of this kind of problem. And at the Joint Quantum Institute, we have other groups like this one that are similarly devoting themselves to different aspects of these problems. And all over the world, there are similar groups studying this kind of stuff. So it's the fascination with this aspect of quantum mechanics has spread all over the world, and we're having a great time doing it. Thanks very much. So I'm happy to answer questions, and just as a special, yeah, if you could go to the microphones, everyone who asks a question gets a prize.
You said about being from this position or this position.
Yeah.
But they are both in our superstition of both states, right?
Well, yeah, that's right. Each spin, this is in the entangled pair. Each spin is in a superposition of being up or down, but it's more complex than I could have had one where this is in a superposition of being up or down, and independently, this is in a superposition of up or down, and if I did something and measured this one, it'd have no effect over here. That's just another kind of possible state, but then it's not entangled.
Yeah, but when you talk about the electron gun, can be both ways.
Yeah.
But when you measure, there's only one.
You only get one, that's right.
This may be because they are flipping in a very speed way, or they are
No.
not flipping. Why when you measure?
Okay.
Is in one position? And
Yeah.
when you
So here's the way in which you tell that it's it's both at the same time, instead of being either one or the other, or in the case you described of constantly flipping between them. It has to do with something that I hid and didn't reveal when I was describing this business of entanglement. So let's go over to here. Okay. So now this this state that shows the actually I don't even want that one. It's simpler than that. It's the okay. So I haven't actually. There's no blackboard in here. What a terrible thing. There's no blackboard. Okay, so I'm going to try to do this way. Okay, no, here we go. Here we go. This thing is in a superposition, right? So it's down plus up. Now the point is that this plus sign doesn't have to be a plus sign. It could be a minus sign, or it could be a complex number with unit magnitude. So it could be e to the I phi. Okay. Now if I know what phi is, then there's something I can do to this state that after I do it, every time I measure it, it'll be in this state. So what I do is, to see that I've got a superposition, I make this state, and then I measure it, and I find half the time I get up and half the time I get down. And then I make the thing I make it 1,000,000 times, and half of those 1,000,000 times I measure it to see whether it's up or down, and then the other half I put in the thing I know is going to fix it to make it, when I measure it, all be down or all be up. And I could use different operations, and I can tell exactly what this number is here. Now, if it were just a mixture, some of them were up, some of them were down, and they were that before I measured it, it wouldn't behave that way at all. It would always end up being half up, half down, no matter what I did to it. But if it's this thing called a coherent superposition, then I can do something to it, make them all be ups or all be downs, and I just have to dial in what, like I send in a laser pulse, and I just have to dial the phase of that laser pulse, and it'll do the right thing. And the process that you're describing is something we do in the lab all the time. We make the thing constantly making transitions between the two, and it's easy to distinguish that process from the one where they're in a superposition. Now, I can stop that process of going back and forth between them in the middle, and then they'll be in a superposition. So it's, in fact, the way we make the superposition is to drive those transitions between the states. But then we stop driving it, and it still ends up in that superposition. And you get a prize. And the prize is a fantastic prize. The prize is a wallet card of the fundamental constants of nature. You see, at NIST, we own the fundamental constants of nature, and we publish this wallet card. So this is you got to have one of these.
My question is sort of an engineering computer problem. If it turns out we can only make quantum computers that have relatively few number of qubits, say 10 to 40, or that's the best we can do, would we be able to change the particle we're using? For example, instead of using an electron that has an up and down state, change it to a particle that's different, that has a wider variety of states, and then up the total numbers we can use.
Yes, so you certainly can do that. That's what people call a Q-trit, if there's 3 states, or and there's some name for a more general one, like a DIT or something, I'm not sure. So you can certainly do that, but the problem is that it doesn't help a whole lot, because the number of effective extra bits is the logarithm of the number of different states that you have. So if I had 4 different states, that'd be like having 2 bits. If I had 8 different states, it would be like having 3 bits. So you don't win very fast that way. And you get your prize.
Thank you.
Hello, thank you for coming, sir.
A pleasure.
Question on what you touched on at the end. You said that there's quite a few teams that are working on actually making a quantum computer.
Seems to be working.
A lot of technology and science is furthered by either government or military work. Is there a push for an actual quantum computer to keep our secrets and to crack others, or is it for the furthering of science, or is it both?
It's both. So
superposition.
short. Yeah. And it's even goes beyond that.
Right.
So at the university we're mainly interested in furthering science, but there are government laboratories where they're more interested in either breaking or keeping secrets. And then it turns out there are a number of commercial companies like Google and Microsoft and IBM who are doing this because they think they can make money. So it spans the range of motivations. And come and get your prize. And bless you for working with service dogs.
Hello. Hi. I have a question regarding how one of these machines would look like. Would it look just like a central processing unit?
Yeah, it probably wouldn't look much like any of the kind of computers we have today.
Okay.
So, and what it would actually look like will depend an awful lot on what physical platform ends up being the right thing. So So for example, let's say that it's ions. Then there's going to be a vacuum system. There's going to be probably some kind of a planar surface with a whole bunch of wires that are connected to electrical power supplies. And then there are going to be a whole bunch of lasers. They're going to be brought in on optical fibers to shine on these things. And there's going to be some kind of a giant mirror array that will be able to allow the lasers to shine on different numbers of the ions. And probably you're going to have a successful quantum computer is going to be a mixture of these different kind of platforms. So you use the ions when you want really long memory, and you use the quantum dots when you want the processor to work really fast. So nobody really knows what a quantum computer is going to look like, but it's probably not going to look anything like the kind of computers that we have today for classical computers.
I have one more question.
Sure.
Do you see any safety concerns with this, like leaking? You mentioned something about these particles can't be exposed to light or anything.
Well, the safety of the particles is, other than the fact that it's really going to be disappointing if these particles see some light that they shouldn't see, it's not going to hurt anybody other than the poor graduate student who slaved away for all these years trying to make the experiment work. And as far as other safety concerns, it's no different from any other sophisticated laboratory where you've got a lot of lasers and vacuum systems and stuff. You take the usual safety precautions to make sure that you don't shine laser beams in your eyes and don't have vacuum windows break and make glass fly across the room. And we've had a lot of experience in making those kinds of things safe. And come and get your wallet card. You're welcome.
Hi, I teach math here, so my question is, what sort of mathematics is necessary or useful in this sort of research?
Well, that's a good question. I wish I knew the answer. See, I'm an experimentalist, and so I don't do the theory for these things. But the kind of thing that you typically need to know is the same kind of thing you need to know just to do quantum mechanics. So. Linear algebra is pretty important, depending upon how you want to do these things. Partial differential equations, that's a good thing to know. Okay,
we teach linear algebra here. Partial differential equations is a bit beyond NOVA.
Well, I think you can do an awful lot with linear algebra. You don't need to do the partial differential equations because everything is isomorphic to a process that just uses matrix algebra. So you may have heard of Schrodinger and Heisenberg. So Schrodinger developed a wave equation for understanding the evolution of quantum mechanical systems, and for that, his wave equation is a partial differential equation. But Heisenberg developed a different method where you use linear operators and vectors, and then Dirac showed that they were absolutely equivalent to one another. So, whatever rocks your socks,
Okay,
you can do it either way.
May I ask another?
Sure.
So if you have these two entangled particles, you move them far away, you measure one, it tells you what's going on in the other one. Can then you change one of those particles and have an equivalent change react from a distance?
No. So people would love to do that because if they could, it would allow them to communicate faster than the speed of light. But there's no way that you can communicate any information faster than the speed of light. You see, you have no idea what result you're going to get when you make the measurement. If you knew what you were going to get, then making the measurement would somehow, communicate. But you have no idea what it is. So there's no information. You've got nothing to communicate before you measure it. After you measured it, this is new information to you. The same information is available to your colleague, but you can't transmit information. It's sad but true. Yes.
Computer in Wyoming. Are you interacting, or this will replace totally in 10 years that type of technology?
Yeah, so the question is, how does this relate to supercomputers, and would this technology replace supercomputers? And the answer is no. This technology won't replace supercomputers. The supercomputers can do a wide variety of things, whereas the quantum computers, for the moment, can only do a few things very well. They can do quantum mechanical problems, they can factor numbers, a few other things. They can't do arithmetic. Well, they can do arithmetic, they just don't do it as well as a regular computer. And most of what a regular computer does is arithmetic. So we're still going to need regular computers. In fact, we're going to need the regular computers even more when we have the quantum computers, because I told you about this error correction where you represent one logical bit with a whole bunch of physical bits. In order to make sense of that, we have to have really fast classical computers figuring out what to do with the information that we get from this error correction routine, and it has to do it, you know, in real time. So we got to have really, really fast classical computers to keep up with all of the overhead that's going on with the quantum computer. So it's not going to put classical computers out of business, except for certain very specialized problems like many-body physics. So people are using these supercomputers to do many-body physics. If we have a quantum computer, the quantum computer will take over doing the many-body physics, but the classical supercomputer will have to act as the service for the quantum computer. So we're going to need both for a long time.
And we'll have to design also curriculum according to all the advances.
Well, today at the University of Maryland, you can take a class in quantum computing, and the stack of books that have been written about quantum computing that could be used as a textbook for quantum computing is at least as tall as I am now. So we're already changing our curricula, and some people, I think ill-advisedly, have decided to teach a first course in quantum mechanics using quantum information as the platform for teaching quantum mechanics. I think it's too early for that myself. But you can just say, instead of saying, oh, you know, here's an electron and a nucleus, and we're going to solve Schrodinger's equation, you say, here's a bunch of qubits, and we're going to see how they evolve under the influence of a bunch of unitary operators that you apply to them. And it's the same physics, but it's a different way of looking at it. And it's a powerful way of looking at it, and people have gained different kinds of insights doing it that way, but I don't think you ought to do that to poor students.
Thank you.
You're welcome. I should give you, yes.
That would be nice, coming from you.
Yes.
Yeah, so about public key encryption, you said, so when someone is trying to break into it, you said they can notice the person breaking into it. How do you get around that? Like,
yes. Okay. So if you've got a quantum communication channel going, then you can tell that somebody is tapping the line. Now, if somebody's tapping the line, then you could then you don't transmit any information that you're interested in keeping secret. So it's a tamper evident. Now, how do you deal with the fact that somebody's tapping your line? Well, you go to another line. I mean, that's one way of doing it, and maybe that one isn't tapped. I mean, I suppose if you run in the right kind of circles, you send somebody out to take out the person who's tapping the line. I don't know. I mean, I'm sure that people who do this kind of work know how to deal with it. That's not my business. You know, it's kind of cloak and dagger.
So basically, I mean, the military is doing active research. I mean, I saw DARPA on there.
Yeah.
So, I mean, these won't realistically be replacing any of the current systems that we are using for decryption and all that anytime.
These are already replacing the standard classical encryption systems for some very special cases. Now, you could argue whether it's needed, but there are banks who advertise that we are transmitting your financial information using quantum encryption so as to prevent the possibility that somebody is intercepting and hacking the information. Now, I think it's just a gimmick, because the real problem is with breaking into the computer system where you've stored all this information classically, okay, not in the transmission. But for really, really sensitive secrets, my guess is they're already doing this kind of thing for some kinds of secrets, but you know, we're not going to know about that. It's been a wonderful pleasure to be with you. Thank you very much.